I will begin. So I will begin with introduction of the CIA organization first for about 10 minutes, and then we will have William start the juice of the talk for today at around like 8 p.m. And then we will have the last 30 minutes roughly for the Q&A. Okay, so let me start with the introduction of the organization. So if you haven't done so, please subscribe our media channel, Facebook or LinkedIn, or any of the channel that you are interested. And we also have a CIE newsletter, QR code. You can scan and you can sign up for the newsletter, and you will be able to know all the important events and announcements. So let me start with the history of CIE. So CIE was founded by some of the pioneer engineers from China back in 1917. And over the years, CIE has grown to have 6 different chapters. And we are the San Francisco Bay Area chapter. And then there are 5 other chapters across the US. And we also have an overseas chapter, OCESA. And we are also holding 3 major conferences, seminar, either in a biannually manner or annually manner. So for AAEOY, we have that annually in the US. And we have METS and SATEC held biannually in Taiwan and also China. For the San Francisco CIE chapter, it was founded 43 years ago in 1917. We are a nonprofit organization serving engineers and scientists and students in Bay Area. And our mission is to promote technology advancement, networking, and also communicating among the engineering communities. So below we have photos showing the annual conference that we have held before in the past, all the way from 1981. And then also the very right photo is showing the annual conference we had in 2019. So since 2020 and 2021, due to the pandemic, we have moved all the CIE conferences to online, virtually. So this is showing that we had virtual conferences, AAEOY conferences, and then we have invited NVIDIA CEO Jensen to have a keynote speech. And then we had broadcast this event virtually, broadcasting online. And then we have over 5,000 people viewing this conferences. And during pandemic, we move all the events online, seminar or tech talks. We have everything online, and then we also have all the recordings. So if you are interested in any of the topics, feel free to go online to our YouTube channel, and then you can find a topic you feel interested in, and then you can watch the seminars again. And last year, we started to resume the first since pandemic in-person annual conference. So we had that in the Santa Clara Convention Center. And then we invited many well-known CEOs and also leaders from the industry to provide speaker keynotes and also afternoon talk sessions. So if you haven't got a chance to join CIE annual conference, we will have one also this year during April timeframe. So welcome to join us and then have a great networking. It's a really great networking opportunity to join our conference, annual conference. And this is showing the conference, annual conference that we had last year. We have many well-known engineers from the communities join the dinner banquet. I think it's over 300 people joining our dinner banquet. And this is showing that the steps from our CIE organization, San Francisco chapter, and also the volunteers that helping us organizing the annual conference event last year. So again, big thanks to everyone who has helped planning on the conference last year. So for anyone who is interested in joining us for this year's conference planning, please reach out to us. And then it's a great opportunity to help us broaden the impact to the Bay Area engineering community. And this slide is showing all the partners and companies who has sponsored and helped us holding the event before. And big thanks to all of these partners and companies as well. And then the slide is showing all the events that we had previously in Q3 and Q4 of last year. So as you can see, we have a very broad variety of events that we are holding in CIE. So not only the technical seminars and webinars, we also have many other like more literature and movie drama related events as well. And this is showing that CIE also has a coding study group. We have this coding study group meeting almost weekly or bi-weekly. So for those people who are interested in coding or who are interested in like switch to the software field, this is a really good opportunity for you guys to have networking to all the software engineers and also learn like interview tips. And also they also offer mock interview experience for people who join the group. So it's highly recommended for everyone who is interested in coding or finding a coding job to join this group. And CIE San Francisco chapter, we aim to bring a positive impact to the Taiwanese and Chinese engineering community. And then besides, like as I just mentioned, besides the technical driven talks and seminars, we also have many like social events as well. So we will do like hiking and also barbecue events. And then we are also looking forward to doing more variety of social events. We are going to have a board game event in mid-March, March 18th. So welcome everyone who interested in learning more in this community and also networking. Please join us on the board game event that we are going to have in March. So San Francisco Bay Area chapter, we have 5 different technical groups. So for today, we will have William from the Emerging Technology Group to provide the talk. And then we also have volunteers, Yan Shu and Meng from Electronic Design Technology Group. Okay, so now it's time to go to the main talk of today. So today the topic is nuclear fusion. So before I hand over the speaker to William, I will provide a brief introduction to our speaker today. So Dr. William Kao received his bachelor, master, and PhD from University of Illinois, Urbana-Champaign. And then he worked in the semiconductor industry and electronic design automation industry for more than 30 years across many big companies in the Bay Area. And then he has more than 40 technical papers in IC-CAD area. And also he's a adjunct professor at UCLA, Electrical Engineering Department. And he's the senior member of IEEE and was also one of the founding members of one second. One of the founding members of IEEE circuits and system. And he's currently teach clean technology and emerging technology courses in the University of California, Santa Cruz Extension, Silicon Valley Extension. And then he has given more than 100 technical seminars since 2009 on various topics. So most importantly, Dr. Kao is a technology watcher, learner, and teacher. So before I pass the speaker to William, please, if you have any question regarding the talk today, please leave your question on the chat. And then at the end, we are going to have a Q&A session. And then we will read out your questions, and then Dr. Kao will answer the question. So please, we are hoping the talk today can be more interactive. So please provide your question throughout the talk, and then just leave the question in the chat. And at the end, we can discuss together on the questions. Okay, so now it's time. Let me pass the speaker to Dr. Kao. Dr. Kao, now it's...
Okay, I'm going to share my screen, but somehow I'm not currently allowed to start the video. So you might want to check about granting me access later on. So let me see where I can still conduct the talk.
Can you share now? Can you share now?
Yes, now, okay, I'll do it now.
Can you share? Or do you need?
Well, let me see where I can still do it.
Hi, Carl. Could you please set William as the co-host as well?
Okay. Okay. William.
Okay.
Share?
Let me to share my screen.
Okay, we can see it now, but you need to make it into the slideshow mode.
Okay, okay. Can you see now?
Yeah, but
Okay.
need to be in the slideshow mode. Right now, we can still see the sidebars on the top and bottom.
Can
Okay,
you see the
that's
full
good.
screen now?
Yes, now it's good.
Okay, okay. Thank you, Carol. Thank you for the introduction.
Yep.
Okay, so good evening to everyone and welcome to tonight's presentation on nuclear fusion. Back in December of last year, I think everybody probably in the Bay Area saw a piece of news from the Secretary of Energy that there was a breakthrough that was done actually locally here in the Bay Area at Lawrence Livermore Laboratory. So I was also very excited to hear about the news and decided to make a presentation on it. Hopefully you enjoyed tonight's presentation. This is the agenda for tonight's talk. First, I'm going to start with the introduction on nuclear fusion, talk about the breakthrough that was done in December of last year, go over the differences between nuclear fusion and nuclear fission. Nuclear fission is the current method that all the nuclear plants are generating nuclear energy. Since the audience is probably going to be a little bit varied, so I'm going to go back to step number one or square one and begin with some nuclear fusion basics, cover some about atomic physics. Then talk about the reason why everybody's so excited about nuclear fusion, the benefits, the advantages of nuclear fusion. Go over a little bit about how this is done. There are two ways of generating nuclear energy. One is inertial confinement fusion, which is the way that actually Livermore Labs did their experiment. And the second one is via magnetic confinement. So I'll go over both of these methods a little bit, just to give you some background about the how. I'll end up the presentation with some of the nuclear fusion challenges and the road ahead. We're basically just at the beginning of this exciting technology. So there's a lot of roadblocks ahead. And then I'll conclude by giving a summary and conclusion. So one thing about people have been talking about nuclear fusion since the 1950s. And from the first standpoint of the hope and the wish is that people were always excited and see whether humankind can actually generate energy the same way that the sun and the other stars in the solar system create energy, generates light and heat. So that was the hope for the last 70 years or so, since the 1950s. Right now, we're already in the 2020s. The others, the negative side is that this nuclear fusion was always deemed to be the energy of the future. And the reason was because it was always like at least 20 years away. By the way, today we're probably not that much different. Hopefully we're a little bit closer and we have a starting point. But we hope that with the breakthrough that was done in December, there will be a lot more money poured in. There are a lot of people who will get into these exciting projects and so on. So let me start with the announcement that was done on December 13 of last year. The Secretary of Energy, Jennifer Granholm, made an announcement that there was a very large breakthrough the breakthrough was that basically you can achieve a net energy gain. Net energy gain means that the energy that you can get out of it is larger than the energy that you put in. Okay. So this was done actually locally here with people who live in the Northern California. This is actually just in Lawrence Livermore Laboratory. There's a branch organization called the NIF, National Ignition Facility. And this breakthrough was done by this National Ignition Group. So let me describe a little bit about what was accomplished in December of last year and what was the breakthrough. So as I said, this was done by the group at the NIF, National Ignition Facility. This is something within the Lawrence Livermore Laboratory, LLNL, so is the acronym for the Livermore National Lab. And basically they achieved fusion ignition. Okay, so the definition for this is that they can, for the first time, they were able to produce a net energy gain. That means that the output energy was larger than the input energy. So this has been the holy grail for many, many years. So a lot of people and scientists have been working on this since the 1950s, but this is the first time that they were able to achieve a Q greater than 1. That means that energy output is larger than energy input. So this took place on December 5th of last year, about 1 a.m. I guess every one of us were still sleeping at the time. And the way that it was accomplished, it was that they fired 192 lasers. And they inputted via the laser energy 2.05 megajoules of energy. And they were able to get out more than 3. Okay, so that means a energy gain. Now, one thing that is not mentioned is that it actually takes a lot of energy to also fire all the 192 lasers. Okay, so really, they did not take into account the energy that was required to fire off all this. So we'll go over a little bit more about it in the following slides. Okay, so it is definitely a scientific breakthrough, but it's definitely not still at the usable stage because you require a lot more energy to fire off all the 192 lasers. So this is a picture that was released by Livermore Laboratories. And what you can see is that all these rays on the right and left of the pellet these are the lasers being fired at it. Okay, and inside there you can see a container that's called the Helium capsule. So just to blow up a little bit so that it's a little bit clear, is that this is what it looks like. So on both the right and the left side, you have all the laser beams being fired at it. So this is the outside capsule. Okay. And so this is inside there. There's this small sphere containing all the fuel. Okay, the hydrogen and deuterium atoms. So just to be able to get everybody on the same page, let me just go back 1 or 2 slides to go over a little about nuclear energy and atomic physics. Okay, not everybody, I guess, is majoring in physics, so let me just go and start from the square one. So when we talk about nuclear energy, that's the energy that is stored within the nucleus of the atom. So that's why it's called nuclear. Okay, and in order to understand that, we'll probably start with defining what the atom, which is the the basic element you start with. And in order to release the energy from the atoms, you can do it one or two ways. You can split the atom and create more than one nuclei, or you can join two or more nuclei and create a larger one. Okay, so we'll go over what that is actually the difference between nuclear fusion, which is the merging of two nucleus, versus the nuclear fission, which is the splitting of a larger nucleus into two smaller ones. So in the nuclear fusion that will be discussing tonight, basically you can fuse together a couple atoms and create a larger atom, and in the process release some energy. So let me show some of this in a slide form. So if you look at the basic atom, so most of you who had high school or college physics, you probably all have had this. The nucleus of an atom is made up of neutrons, which have, just like the word says, is neutral, there's no charge. And then also the purple ones are the protons, which are positively charged. And on the outside of the nucleus, you have the electrons floating, okay, which are negatively charged. So a little bit about atomic physics is that, let me just go to the next slide and show you. The Coulombs Law, everybody probably familiar with that, is that whenever you have like atoms, they will repel each other. So a positive and the positive charge will repel each other, while opposite charges will attract, okay? So a positive and a negative will attract. So as part of the nuclear forces, there are actually two kinds of phenomena. One is that whenever you have two positive charges, they will repel each other and they tend to drift apart. At the same time, in order to create fusion, you need to bring them close enough. And this is done through also based on another phenomenon, which is based on quantum physics, called quantum tunneling. Okay, so let me just show you a couple pictures so that you can get an idea. So quantum tunneling means that usually whenever you want to move a block, okay, and let's say you want to move this block uphill, it takes a lot of effort to move it. One of the properties about quantum physics, however, is that it's called the tunneling phenomena. That means that you can get from one side of the hill to the opposite side of the hill via a tunnel, and then you can save a lot of effort because you don't need to climb the hill and come down the hill. Okay, so this is the quantum tunneling effect that I was talking about. So given the background on the atomic physics, the atoms, the nucleus, the electrons, the protons, and neutrons, now let's go over more specifically about the nuclear fusion. Okay, nuclear fusion, again, as I pointed here on the bottom of the slide, is the merging or fusing of two lighter nucleus to form a larger nucleus. Okay, usually the two that are smaller are hydrogen isotopes, and then the output is a helium one. Okay, and because the final mass of the larger nucleus is smaller than the sum of the two small nuclei, there's an additional amount of energy that is released. Okay, so this is the picture. You have here called the deuterium and the tritium. Okay, and the definition of this is just depends on the number of neutrons. Okay, the deuterium just has one proton and one neutron, while the tritium is two neutrons, one and the proton. And then when they combine and merge together, it produces fusion. And the output is a larger nucleus, which is the helium. Okay, helium is made up of two protons and two neutrons. And the additional thing is released in the form of energy. Okay, so there's also another neutron that comes out, and the remaining, it comes out in the form of energy. And this is the energy we'll talk about that produces fusion energy. Okay, so this is the same, a different slide, but just show you what's happening. Deuterium and the tritium combine, they fuse together, and the output is a helium particle and the neutron and some additional energy that is released. Okay, so everybody knows that right now there are a lot of more than several hundred nuclear plants around the world. So all the nuclear energy that is being produced right now is done via nuclear fission. Okay, so in the next slide or two, I'm going to go over the difference again between the fusion and the fission. So the topic that, well, let's start with this one here. The nuclear fission is the current method for generating nuclear energy. And the fission is actually splitting a larger molecule into two smaller ones. So this is the way that is done currently in all the nuclear plants around the world today. The new technology that people are getting excited about is nuclear fusion, which is combining two smaller particles and creating a larger one. Okay. So I think in one slide, basically, it illustrates the difference between one is joining and merging two smaller ones into a larger one, and the fission is splitting a larger one into two smaller ones. Okay, now, why is people so excited about nuclear fusion? So there's a lot of benefits and advantages for nuclear fusion. Okay, so let me go to the next slide and come back to this one. These are the three main principal reasons why people will get excited. Number one, nuclear fusion produces zero energy greenhouse gases. Okay, so it's clean. So it's like a clean energy. Number two, there's almost no radiation. So basically it's safer than compared, say, to the nuclear fission right now with all the remaining remaining waste, right? Second, the third one is because they're unlimited amount, because actually in order to produce the hydrogen isotopes, you can extract it from seawater. Okay, so we all know that 3/4 of the planet is made of sea, right? Is of water. So there's abundant elementary input to generate nuclear fusion. Okay, so these are the three main reasons. It's clean, it's safer, no radiation, and the third one is because it's very abundant. It's almost unlimitless. So let's go back to break down a little bit about the specifics. So if we have nuclear fusion in the future, is that there is no more need for fossil fuels. Okay, there's also no greenhouse gases. Okay, as I mentioned, it's unlimited availability. Okay, because you can extract it from seawater. The other thing is that it's much more controllable. So basically the thing was shut down by itself, okay, unlike the nuclear fission technology. And it's not radioactive, or it's less radioactive, although it does produce a lot more heat, okay? So you can see that there's a lot of benefits, and that's the reason why they say that's the holy grail for people working on the energy field. Okay, now disadvantages. At the beginning, I mentioned that in the Lawrence Livermore experiment, they were able to achieve a net energy gain. That means that the energy output is larger than the energy input. Well, it still does require a lot of energy. As I mentioned, in the one of the methods that was used in Livermore, they had to fire more than close to 200 lasers, okay, to ignite the particle. Okay, now the other thing is that right now, because right now there's currently no nuclear fusion plants and so on, is that for this to happen and be able to generate electricity to the grid, we basically have to create a complete infrastructure, okay, which will be different than the current infrastructure for the current nuclear plants. Okay, so we are really at the beginning of the road. So it will take, I think that it's good that we achieved the first milestone, but in order to make it so that it's productive and effective, it probably still lies a lot of obstacles and roadblocks ahead. Okay, and the main thing, of course, is always to say, can you make it cost effective compared to the current solar and wind energy and fossil fuels? Another challenge is that all of this is done at very high temperature. So in order to generate this, this high temperature effect, it requires a lot of special technology that we'll be talking about next in the how process. Okay. So this list, so we briefly described what is fusion energy and why people get excited about it, what the benefits of them are. Now let's discuss a little bit the how. Okay, how this is produced. So there are two basic methods. One is called the magnetic confinement, and the second one is the inertial confinement. So the one that was utilized by the NIF was the inertial confinement fusion method. We'll go over that, describe each of these two. So the magnetic confinement fusion basically is done via a device called the tokamak. Okay, the tokamak is a donut-shaped vacuum chamber, and it's actually done by controlling very powerful magnets. Okay, and you can generate super high temperature plasma. So this is look at the temperature, 150 million to 300 million degrees Celsius. So this is the way that actually energy within the sun, this is generated. And in order to achieve such a high temperature on Earth, you need to do a lot of special technologies, so you have to go and generate some plasma. The plasma, besides the three states that everybody's familiar, the solid, liquid, and the gas, there's a fourth state called the plasma. The plasma is where basically you have a ionized substance, and because it has specific electrical and magnetic properties. Okay, so that's something that, again, it requires a lot of effort, and that's one of the challenges lying ahead. Okay. The second method is called the inertial confinement method. And this is by firing laser beams, okay, at a small capsule. So inside the capsule, there's the deuterium-tritium thing that we described in the atomic physics part of it. So if you look at it, for the Livermore Laboratory experiment, it took 192 beams. Okay, so definitely you cannot produce a plant or a device that can generate energy if you require such a large number of lasers, right? So either the efficiency of the lasers has to improve tremendously so you can cut down on the number of beams. Okay, and the other thing is that you need to make sure that this can be repeated, very frequently. It's not like, it took a lot of effort to generate that experiment. So if you want to make it a electricity generator, you need to be able to do it, every minute, right? Okay. So let's just go over. I'm not going to go too much into the details because not everybody is a physics major here, but I just want to just show a little bit about what the two methods are. So in the magnetic, this is a device that actually originally was invented in Russia way back in the 1950s and 60s. Okay, so basically you use the magnetic field to control the plasma, the temperature and the pressure of the plasma. So I'm just going to mention here, there's basically the toroidal effect that goes around it. And then one is the poloidal field, which is the north and south. And the two combine and generate the two combine and gets twisted and generates a magnetic field that confines the particles in the plasma. Basically, you control it so that it remains in place. And then the third one, there's a third field that's on the outer poloidal field that shapes the position and the shape of the plasma. So this is in a very long words here. Let me just show you in a picture form. This is what a tokamak looks like. Okay, so we mentioned that there are three fields. One is the one in green, okay, is at the poloidal, north and south. The toroidal that goes around it in blue. And then the final one is in black. Okay, so you won't get a quiz on this, so since everybody, but I just thought that it might be nice to show you a picture what the thing looks like. Okay. Now, the second method is called the inertial confinement method. This is the method that was used at the Lawrence Livermore Laboratory. So either ion or laser beams are being used and fired to this container. So this is the actual container, the size of the container. You can see that it's very tiny. So you can compare the size of this whole room and the capsule compared to the size of the finger. So it's a very small device. So you have to aim the 192 beams into this capsule. And remember the initial pictures where you had the laser beams shooting from the right and the left into this small, this is only about like 1 millimeter size, okay? So it's a very small device. So the best way to do it is either by firing lasers or ion beams. Okay. So this is just show you in picture form. So here the rays are all laser beams that being fired. Okay, and then once the thing is fired, then it creates the tremendous amount of heat that is required. Remember that I mentioned that it requires over 1 million degrees Celsius. So this is done by striking laser beams into this deuterium and tritium capsule. Okay, so again, this is just a step-by-step approach. I just show you, but I don't think you need to go, and not everybody is going to become a nuclear physicist. So, but this is just to show you that the laser beams are being fired. You can see that the two sides of the capsule and where the laser beams come in, and then this thing goes into the thing, and then at the end, basically you generate and do a implosion. Okay. So if for people who are interested, I'll be glad to send you over the detail of the paper about how this is done. But for tonight's presentation, since we're talking about a much more general audience, I'm not going to bore everybody with a lot of nuclear physics here. All right. Okay. So what are the current efforts regarding nuclear fusion? Okay, so there is different organizations, large and small. So let's talk about the largest effort. That is a joint effort by 35 countries. This is called the ITER project. The ITER project right now is based in France, and there are more than 35 countries contributing scientists and faculty to make this happen. The output of the ITER is not going to be like energy, but it's actually, they are going to traverse all the issues that they are going to be facing, okay? So it's a multinational effect, a project. The countries, among others, all the big countries like China, US, and Russia, they're all in there. India, South Korea, Japan, and UK. And of course, France, because this is where physically the ITER project reactor is located. So the goal of ITER is not really to produce electricity, because we're still very far away from being able to do that. But basically is that you pull all the scientific resources from many countries, and together they're trying to solve some of the scientific and technical issues that they're facing right now. So this is more or less the ITER, what the reactor more or less looks like. It's a very large size, it's a very large complex where all this is housed. Here on the right side are all the principal countries that are participating, including the EU, China, India, Japan, Korea, Russia, and the US, okay? Okay, so that's what's happening on the global stage, where countries and governments are collaborating to resolve some of the critical issues. Now, recently, there are a lot of all the billionaires, okay, the Jeff Bezos and Elon Musk and Bill Gates and so on, they are also very interested on the nuclear fusion. So they are heavily investing their money into startups. Okay, so we'll just go over a few of them, the 4 top ones. Right now, according to Forbes, there are 33 companies that are working on nuclear fusion. Okay, and they have basically at least $5 billion that are going to be financing some of these startups. So as I mentioned, all the billionaires are into it. I guess besides the ChatGPT, people are, and AI, people are also very interested in this effort. So Jeff Bezos is investing in a company called General Fusion. Peter Thiel is investing in Helium Energy, and Paul Allen is into Tri-Alpha Energy, TAE, okay? So I'm going to just say a very few short words about each of these companies and how they are approaching this effort. So the first company is called Tri-Alpha Energy, also called TAE. And former Microsoft co-founder Paul Allen is actually investing a lot of money into it. Okay, this slide actually just shows the 3 billionaires, or 3 or 4 billionaires involved into different companies or startups. One is Tri-Alpha Energy, Peter Thiel is in Helium Energy, and Jeff Bezos in General Fusion, which is a Canadian company, and Bill Gates is investing into Terra Power. Okay, I think it's somewhere in Wyoming. So let me just quickly traverse these private ventures. So first one is Helium Energy. So they are building a reactor called the fusion engine. Okay, again, it uses helium along with the deuterium from seawater. As I said, they're trying to tap from the seawater. You have basically a lot of hydrogen isotopes that you can create from that. And this is based in Washington State, Redmond. And right now there's at least 5 million, various amounts of this. Probably this is not all of it. You can have different, there's probably usually about 4 or 5 venture capitals that are invested in each of the company. So it does take a lot of money to work on nuclear fusion, okay? So this is a picture about Helium Energy's fusion engine. Okay, so this is not like a small gadget, right? So it's a very large device. The second one is TAE, Tri-Alpha Energy. This is based in the Foothill Ranch, California. And they use a technology called aneutronic fusion. Okay, this is actually done by releasing this done via the neutrons. One of the founders was called Norman Rostocker. So their device is called the Norman. Is their new device, the generator device. And a lot of the startups, by the way, if you look at all the advertisement and technologies, things that they're releasing, what they are working on, they are shooting for around having some capability by the year 2030. Okay, I think, in my view, I think it's a little bit optimistic, but it's good to have a challenging goal, right? So you can see more or less the size of the company, 250 employees, and currently already raised over, close to $1,000 million here. Okay, so this is the Norman. Okay, the Norman is the device name from TAE, and you can see now these are really small things. So they are very large devices, a large equipment, and even this right now, I'm not sure, in order to achieve something that can be utilized for energy generation, it may take a lot of additional work. So, but basically, there are a lot of startups working on it, because that's a good sign, because you have to start from step one. So unless people start investing money and so on, you're never getting to the end. And right now, because of the breakthrough that happened in the Livermore Laboratory, I think it's probably going to make it a little bit easier to find more funding, because people say, well, look at it, and then there are so many startups already working on it. As I said, there are more than 33 startups working on nuclear fusion. So definitely people do have very high hopes that it will make it someday. Okay, hopefully in my lifetime. Okay, the other company is a Canadian company called General Fusion. And Jeff Bezos is the one that is putting money into this effort. The company was founded by Michel Laberger, and currently has also about 200 employees. So you can see that the size of each of the startups, about 200 to 300 scientists. Okay, and then this is something that is not just limited to that particular facility. It's always working with somebody else around the globe, so there's a lot of effort in the UK. Okay, and as I mentioned, there are more than 30 countries working on nuclear fusion as part of the ITER project. Okay, so this is what the General Fusion gadget looks like. So you can see it compared to the size of the human, how big this thing is. The one that Bill Gates is involved is called Terra Power. Okay, and right now it's located in Wyoming. And the name of their device is called Natrium Reactor. Okay, the Natrium Reactor. All these companies, they are also working with the US government. So there's a lot of good collaborative work between the private sector and the government. Okay, and here he also mentions that he's not only working with that, but he's also working with some other Japanese companies like Hitachi and so on. So this is what the Natrium Reactor from Terra Power looks like. Here, let me just check on my time here. Okay, looks like I'm exactly on schedule. So this is the last and probably the most interesting, what lies ahead. So I think that just to summarize up to this point is that I think that the breakthrough that was done in December was very good, was very encouraging, and it's going to help startups and getting more funding for the bigger projects because they see the promise, okay? There's a hope that this thing one day will make it and we can generate energy via nuclear fusion. We already mentioned what are the benefits of nuclear fusion. It's safe, it's clean, and it's limitless amounts of thing to generate the nuclear fusion. So where do we start? As we can see from all the presentation up to this point is that almost every country have physicists and scientists working on this technology, okay? On the other hand, the problem and the challenge for this technology is so huge that I don't think that without any collaborative effort between either government and the private sector or among countries, you are able to achieve and lick all the challenges that are laid in front of the things, okay? We'll mention about what are some of the challenges in the next few slides. It definitely looks like it will require a global partnership and collaboration, okay? The other thing is that in order for this thing to make it, which is like to be able to generate electricity from nuclear fusion, a whole entire nuclear infrastructure needs to be built, okay? Because nuclear fusion is quite different than nuclear fission. So you need to be able to generate things at a very high temperature. You need to find new elements that can sustain that high temperature and high pressure, okay? You need to build a very large magnetic field and so on. So in terms of timelines, how close are we from being able to get something out of it, which is going to benefit, you know, our current society? There will be a lot of accomplishments and breakthroughs between now and say 2030, but I don't envision that within 10 years, we're going to be able to see something that can be used, you know, to generate electricity. So I would say 10, you know, well, at the beginning, we said that nuclear fusion was always the energy of the future, but at that time, they were talking about 20, 30 years away. Right now, maybe we're one step closer. Maybe we're taking maybe 10 years or between 10 and 20 years. Nobody knows, okay? Because there are a lot of problems that probably we are not even, have not identified what the problems are yet. One of them is that it takes a lot of energy just to generate energy. The other thing is that you need to find materials that can withstand such high temperature and high pressure. So what are the issues that lay ahead? Well, we mentioned at the beginning that in the Lawrence Livermore experiment, it took close to 200 laser beams, okay? So you need to be able to produce something much more effective. And instead of firing hundreds of lasers, maybe can we do it with 2 or 3, you know, because otherwise it's not going to be productive. Okay, it's something like a scientific experiment, but it's not really like an engineering accomplishment, okay? So we were able to get the gain greater than 1. That's great. But we, as I mentioned in one of my previous slides, is that we ignored the energy that it took to fire the 200 laser beams, okay? The other thing is that in order to be able to generate electricity, you keep to have firing this every few seconds. So it's not like do it once every 10 years or do it every, you know, very long period of time. It needs to be firing and igniting the thing almost on a second by second basis. Okay. And like any technology, in order to make it useful to society, you need to bring the cost down. So how does the new nuclear fusion technology compare to the current nuclear fission nuclear fission plants, how does it compare against renewable energy, solar, wind, hybrid, fossil fuels? Okay. So you have to make it commercially viable. Okay, that means that it has to be something that the cost is acceptable. Okay. So again, some of the challenges here, I'm just sort of reiterating some of this, but what are the roadblocks ahead? Okay, you need plasma with temperatures that are exceeding 100 million degrees Celsius. You need the, like if you use the tokamaks, you need to have very large magnetic fields to be able to control and confine the temperature and the pressure. Okay, you need to continue to be searching with for new materials and new mechanisms. You need to make the lasers much more efficient. Okay, and not only that, but you need to build a new infrastructure around the plants and how can you produce energy from nuclear fusion. So, summary and conclusion. Let me see. We're very close to 8 o'clock, so I'm right on time here. So I think that last December, I think it was a very major breakthrough, and it's sort of like makes people working in this field more excited because at least there's a little like light at the end of the tunnel. There's a lot more hope. And they're able to lick a problem that has been around for more than 50 to 70 years. Okay. We already outlined what are the advantages of nuclear fusion. What are the, like clean, safe, and abundant, right? That's really the three major points about nuclear fusion. And with this breakthrough, I think that people, hopefully not only the billionaires, but a lot of governments and so on, they will be willing to spend and fund some of the new projects and new efforts. Okay. So the road ahead is very long. There will be more breakthroughs and more significant accomplishments between now and say 2030. Hopefully, all the startups may make some claims, say, okay, now we are able to do this or do that. And hopefully all of this will generate more excitement toward this field. Okay. But the challenges, the ones that I mentioned in my presentation, it may be just the tip of the iceberg. There are probably a lot of problems and challenges that we really won't know until we hit them. Okay. So in terms of time-wise, like people ask me, well, when is the metaverse going to become a reality, and so on. So some of this, it may not be in the next 2 or 3 years. Right now, if you look at the current assessment of this technology, it will be at least about 10 years. So we're right now 2022, 2023. You'll probably be at the earliest in the 2030s. Okay. And who knows, if we run into a roadblock, it may take another 20 years. Nobody knows. Okay. The other thing is that we need to distinguish between a scientific breakthrough versus something that's engineerable. Okay, something that actually we can use, not just something that can be produced in the laboratory, but something that has to actually impact on current society. Okay, so this is the end of my presentation. Before I open up for Q&A, let me just give you a quick preview of the next talk that I'll be giving in March. Okay, so besides nuclear fusion that came out in December of last year, another thing that came out in December or end of November last year was ChatGPT, right? So my next talk, if you know, God allows, is that it will be in March, and you will be the title of that seminar or webinar will be Next Generation AI. Okay. So things that will be covered in this particular seminar in March are the following. So we'll go over some of the latest technologies in AI, like unsupervised learning, federated learning, transformers. Transformers is what the you know, ChatGPT and this thing is about. Edge AI, neural network compression, generative AI. Generative AI and transformers are the ones that right now is causing, you know, the whole, you know, I mean, it's hot everywhere, no matter what field you are in. The people say this is the next, you know, best thing since sliced bread, right? So also generating data, synthetics for data. We'll cover a little bit about ChatGPT and GPT-4, which is the next version of GPT. We'll cover also a little bit about the AI wars. Right now, since it came out, people say, well, maybe Microsoft will pose now a challenge to Google. Okay, so that's going to be, the presentation is actually already prepared, but it will be next month before I present it. So in between, there's going to be several iterations to the material. Okay, so with this, I'm going to turn it back to the host and open up for some of the Q&A.
Yeah, thank you, William, for providing such a high-level introduction of the nuclear fusion technology. That's very informative. Thank you. And I think now it's the Q&A time. So let me see. I see there's one comment.
Okay.
Joe. It's not a question, but it's a comment.
Okay.
I think Joe is trying to say firing 192 laser beams are quite feasible. The Athos cancer machine by Varian can fire nearly 2,000 guns one time at 6 math. Maybe William, do you have any comment on this?
Sure. I agree. I mean, right now it's feasible. I mean, it was done, but it's done within the confinement or within a scientific and a laboratory. So in order for it to be useful, you cannot go and say carry guns that can fire 192 beams or any number of beams. So what I'm saying is that right now we need to, again, the thing that one of the points I was trying to make is that we need to distinguish between a scientific accomplishment versus a engineering accomplishment. And right now, only engineering things are usable, not things that are done in the laboratory.
Mm-hmm. So any other question from the audience? Oh, I saw one more comment from the audience. So do you think that this new technology will be able to significantly impact climate change and the rising temperatures?
Okay, yes. The answer is yes. And I mentioned it in my advantages slide that it says does not produce any greenhouse gases, right? So it's clean energy. So climate change is being affected because of all the, you know, greenhouse gases and so on. So if we go into clean energy, solar, wind, and nuclear, then that will cut down on the carbon emissions. Climate change is being affected because of the blanket around the Earth, planet Earth, caused by carbon. So yes, there definitely, and that's the reason, as I mentioned, the three major benefits of nuclear fusion is clean, is safe, and it's abundant. So when I say clean, means that it's clean. That means that you have less impact on climate.
Okay. Thank you for the great explanation. I see more questions coming out now. Question, nuclear fusion is very difficult to do. Is there any chance for startups to work on? Such as startups can provide a part of nuclear fusion engine system?
Yes, the answer is yes, because as I mentioned, there are 3 startups working on nuclear fusion. So everybody has a hope that whatever their company is working on will make it, because whatever company makes it, there's a lot of money, involved, right? So you're going to make a lot of money. The first one is always the one that makes the money. I think I saw also another question about regarding the substances and materials. That to me is actually the solution to many of the problems that we face today. So I always get a lot of young people say, well, what is a good field to get into so that my job won't get displaced in another 3 years or before I graduate? One of the areas is material science. So all of these efforts will require, for instance, right now, EVs, you have to move from lithium to another material. Okay, so all of the answers, many of the answers lie in material science and finding new materials or making new composites of new materials.
Okay, so I think that also answers Vincent's question, right? Could the material be deadly constraint to commercial nuclear fusion?
Could the materials be a deadly constraint? Is that the question?
Yeah,
okay.
Vincent's question is, could the material be a deadly constraint to commercial?
Well, I would answer this question just by turning the question around. Okay, so instead of finding a material that is going to be like a limiting factor, what you need to do is to find an element that will do better than the current portfolio of elements. Just like, for instance, batteries today are still not up to snuff. Okay, so can you find what's the next element besides lithium ion? Okay, so the challenge is not to just find any element and find out that it has a problem. What you need to do is to find something that will circumvent or be better than the current elements that are being used.
Okay, I don't see more question from the audience now. So maybe I can ask a few questions.
Sure.
So based on what you just provide in the talk, right? It seems like the whole nuclear fusion is still a very far-fetched kind of a technology, right? It's still gonna take another 10 to 20 years before we can actually make a commercial use. So do you think so it seems like even more far-fetched than like the virtual reality that we are talking about, like for the AI and VR, right? So do you think this is really going to be one day like really possible for commercial use, or it's gonna be like a hype, like people are chasing this idea, but at the end found out that it's actually not really cost effective, given that there are a lot of like obstacles to build all these machines to make it efficient? Like, what's your stand on this?
Okay. Since my area of expertise is called emerging technologies, so I cover all of the above. I've given talks on 5G. I've given talks on the metaverse. Okay, I've given talks on satellite communications, and today I'm giving the talk on nuclear fusion. All of the above are what new startups or new companies or they're putting a lot, as I said, all the billionaires. If you look at what the billionaires are doing right now, they are all investing in satellites, right? They're going to space. Okay, they're also investing into some other ones, like unfortunately, with Facebook and the metaverse. Right now, they have some setbacks, but it doesn't mean that all of the things that nobody has a crystal ball. Nobody knows in 10 years time frame which of these technologies will make it and which ones will fail. Okay, But people who have money or a lot of money, they are betting on it. So guess what? All the ones that you mentioned, they are all people working on it. And they're all people putting millions and millions of dollars into it. So the thing is that nobody can guess the future. So people cannot say, well, let's just stop right now. Because one thing is that, for instance, nuclear fusion, the people have been working on it since the 1950s. Now, there's nuclear plants today. So when you say that, if it's not doable, well, how come nuclear fission was able to do it? So, but the thing is that until you hit the last roadblock, nobody knows whether we're going to succeed or not. Okay, so it goes with the answer with the metaverse. So it goes with the 5G, which is going to go from 2020 to 2030. Nobody knows about EVs. Nobody knows about batteries, right? I mean, so, but a lot of people, all the startups are based on hope. If you go and form a startup tomorrow, you say, well, hopefully my company will make it and I become a billionaire. Right? So everybody has hope to make it. And these are things that it's not like a wild bet, because if you look at it, all the people who are putting money into these efforts are the ones that actually succeeded in one form or another. Bill Gates, Elon Musk, Jeff Bezos, all these people, they succeeded in the past. Now they are betting on this type of technology. So it's just money down the drain, because nobody has money that you just want to throw it away, right? And then from a country standpoint, every country wants to be able to do it first, because they will control the energy in the planet. So right now, for instance, who controls the resources? The Arab countries, because they got the fossil fuels. Everybody still relies on oil and gas. Okay, so if one day nuclear fusion makes it, then people will select nuclear fusion because it's clean and safe.
Okay. Yeah, I see one more question from the audience.
Sure.
So, what is your definition of metaverse, and how specifically can nuclear fusion help building real metaverse?
Okay.
Like providing computing power for metaverse?
Okay, so let me answer the question, since I make the claim that my emerging technology is my field, so it's not only nuclear energy here. Okay, so let me just answer the first question first. What is the metaverse? Okay, so the metaverse is actually a combination of augmented reality. Okay, reality is what we see around us. Okay, what we see around us is reality. And then virtual reality is what doesn't exist around us, but we can make it so that it helps reality. So once you put on some headset, now you go into the virtual world. Okay, so metaverse is the combination of all of the above. It's the combination of the reality or physical reality and virtual reality, and trying to leverage both. So the metaverse, in a definition, if you want to go and try to pictorially vision what's the metaverse, right now, planet Earth is called the physical world. It's where we live in. Okay. Now, in parallel to the physical world, there's another world. It's called a parallel world, and that's called the virtual world. Okay. Now, eventually, they will complement each other. Okay. Hopefully, the virtual world will assist also a lot of efforts in the real world. So the metaverse is really the combination of all of the above. Okay. Now, to try to tie nuclear fusion and metaverse. Okay, so the way that he actually provides the answer in the last sentence. Okay, if one day nuclear fusion becomes a reality and there's unlimited energy, then it will help the metaverse and it will help ChatGPT. So if you look at ChatGPT, what's the constraint today? You know how much compute power it requires to answer everybody's answers? I think they estimated like $3 million a second, because that's what the OpenAI is contracting Microsoft Cloud, Azure, because it takes computing power. So computing power takes energy. So that's the connection. So if one day we have unlimited energy, then you can have unlimited number of computers and compute power. And unlimited compute power means a better AI and better metaverse and so on.
Yeah.
I like the questions right now. They are going beyond the nuclear fusion because not everybody is a nuclear physicist. So but it's good that people are asking how does it relate to all these other technologies, because there's a lot of synergy between all the new technologies that are around.
Yeah.
Today.
I think there's one more question from the audience. Could this technology outside their use for industries be used for more basic use, such as power cars?
Sure. As a matter of fact, that is already available today to power cars. Have you heard about the hydrogen power cars? Okay. The hydrogen power cars are actually very similar. They use a form of hydrogen, like the deuterium and tritium and so on, to power. They use that as the energy to power cars. So today, the cars are moving from fossil fuels to electric battery power cars. And right now there's actually several companies to already have hydrogen cars. But that's a topic for another seminar.
So maybe let me make this question more specific. So how does the fusion, like nuclear fusion, be used to power cars, right? Does that mean like there will?
It's not being used. It's not being used because right now there's no nuclear fusion energy right now. So you're asking a question that is like 10 years in the future.
Yeah, in the future, how do you imagine that will be used by the car? Is it like there is a small reactor in the car to produce the energy? Or what's your imagination of?
Okay, let me answer. Okay, how does electric cars get charged today? You park your electric vehicle in the garage and you plug the outlets into your electric vehicle, right? So it's not like you need to carry a reactor inside the car. But once you have, see, right now we are not at the stage where you can deliver electricity to a house via nuclear fusion. Once you have the thing in your garage, you can just connect your garage outlet to the car. That's the way you do it. You don't need to have everybody carry a reactor inside the car. That's not realistic. It's just a fuel. Remember that this is just a fuel. Right now, you don't carry a gas pump inside your car. You go to a gas station and you pump gas into your car, and then you can run until you run out of gas, then you add more. Okay, when you use an electric vehicle, you go to the charging station and you charge the car. And when the battery run out of electricity, you go and charge it again. So that's the same way. It's just a fuel. It's not like you need to carry all the world's fuel in your car.
Yeah. So just to make the question more specific, so it will be used as a way to charge like either a like electric car that we will have in the future.
That's right.
Okay? So,
that's right. And also you have to think a little bit out of the box. So today you have a plug, you have an electric outlet in your garage, right? And you connect it. Nobody knows when the nuclear fusion is available, there may be a different outlet. Like for instance, right now in your home, when you do the washer and dryer, that's a different outlet than it's not your regular 60 kilohertz outlet. Okay, so nobody knows when you have a fusion energy, it may be another type of connector that can connect to your car. Okay.
Okay, so let me see if there is any more questions from the audience.
So again, I want to thank all the audience for tuning in to tonight's seminar. I also want to thank the CIA volunteers for hosting the event, and also to provide all the IT support for this event. I want to thank all the audience for their time to come in and listen. So hopefully everybody gets something out of it.
Yeah.
And
So,
till the next month.
yeah, thanks, William, for this amazing talk today. And I think, yeah, as William just broadcast, like we will have another seminar next month talking about ChatGPT. Hopefully, we will see everyone in that seminar again. And then also special thanks to the volunteers today, like Yan Su and Meng for the helping. And then thanks the speaker, William, for the wonderful talk today. So hope to see you guys in the future CIE seminar. So I think this end of the talk today. Hope to see you guys in the next seminar.
Okay, thank you. Thank you, everyone, and good night.
Thank you.
Okay.